Interactive. Okay, so I basically have nearly finished. So maybe let me try some interaction now. So maybe if you find something here, something interesting, maybe so they get this. So the question, if you have a knot, the question is knot of what in physics? So we need some one-dimensional structure to make a knot with. So what kind of structures you could consider in microscopic physics? So there are some one-dimensional structures considered, like in these quark strings, for example, yes, QCD. I don't know. So yes, so there are these quark anti-quark strings, and there is some string, and there are some created some pairs, pion, I think, from this string. There are some string again. So there are these one-dimensional structures in Sans corona. They have literally this. They see there is sans surface, and they see these shining lines, and they form some complicated structures. And these are not. They make these reconnections, which destroy topology. So magnetic reconnections. So the assumption that topology is satisfied is usually broken. It's often broken in physics. But they have this. In practice, they can reconnect these objects. Yes. Also in knot theory, you assume that they are not broken. These one-dimensional structures, but in physics they are often broken. So there's any question how high energy is required to break it, for example. So literally they reconnect. And thanks of reduced this length, there is energy density per length. So thanks to reduced length, there is release energy. They observe shining one-dimensional structures. So I don't know. I don't think I'm continuing. So I haven't finished. So if you have found something interesting, I don't know. So discuss here on. So what kind of knots you are interested in? Of what objects, physical objects? Yes. So that's the question.
You had some knots in particle physics, or?
Yes. Yeah. So there are assumed these quark strings. There are assumed in QCD. Yes, for example, there are assumed cosmic strings. That this quantum phase makes 2 pi around this. So there is in cross section that there is topological charge. So there are assumed some one-dimensional structures in physics. Also, this microscopic in superfluid superconductors. There is one. So there are nice one-dimensional objects which can form knots, but sometimes these knots are destroyed by reconnections. Yes. I don't know. So I have basically finished. So I don't know. So if I was expecting some interaction, so usually there's not much more if there is interaction.
Okay, so let's thank our speaker. Yeah, maybe you have some more questions now. I have maybe a question. How this description in terms of knots what is the relation between this description in terms of knots and standard QCD? You try to derive QCD from this knot description?
Yeah, so that would be ideal, but there are not quarks. So there are some kind of quarks, some fractional charges. They are enforced by the structure that is loop around, and forces some part of the hedgehog, which the full hedgehog is the +1 charge. He is, let's say, 2/3 and -3. So we can see that this confinement that you have Gauss law that asymptotically there are integer number of charges, but locally this hedgehog, this topological charge can be deformed, for example, by some by this loop here, and so from experimental perspective, there is also charge distribution, which is for Newton is positive core, negative shell, as here. So I can directly try to agree with this kind of predictions. But finally, there should be effective description by this kind of fractional charges, by some types of evolutions. So to finally not having the full description, we need to go to Fermat ensembles of possibilities to perturbative QFT. So that's the final goal, but I'm not so far there because it's quite difficult. So to find that's the standard model Lagrangian, and the question is, could we find something simpler for which this is only some Taylor expansion? So that's the main goal here, to find some simple model, like topological, which effective description becomes this something close to this standard model Lagrangian. So here is my approach, that's just to expand electromagnetism, and this unifies also the quantum phase and the gravity, and effectively gives these three charges, electromagnetism, with charge quantization, also the proton related neutron, and many others. But it's very difficult to get to show that it's effectively described by this kind of relation. So that's the main point. But I'm not so because it's very difficult. So these are not knots; these are field configurations, which are effectively described by knots.
Mm-hmm. You also mentioned that you do some computer science research, and is it related directly to what you described today, or is it another branch?
Oh, completely another. So I'm known.
Okay.
So I'm known for asymmetric numeral systems. So I'm known for ANS coding. So which is used like in every smartphone, every computer now uses my coding. This I'm known for. Mm-hmm. But I have also PhD in physics and so on. So I do many types of research. So your smartphones probably encode with my method.
Yeah, very nice.
But I also have PhD in physics, and I also do foundations of quantum mechanics and particle physics. So and this skeleton model is like for 15 years, but it's very slow research.
So a term vortex knots appeared on the vortex. Is this some definitely described class of knots?
So they get these one-dimensional structures. For example, there are fluxons are because of vortex in superfluid, superconductor, but also in optics. They can get that the quantum phase makes a 2π rotation around some line. So there are some structures, and they can get knots more or less complicated with them, and they stimulate them with some differential equations, but they are often not stable knots that they can reconnect, for example. Yes.
So it's not a knot as it is.
Not ideal topological knot. Yes. So we need to include energy. That there is some problem. With high energy, you can destroy its knot, or maybe it can reconnect itself. So, for example, this is one of the directions I'd like to go. That if baryon is a knot, then maybe you could destroy this knot. Yeah. So here is. So if baryon is a knot, then maybe we could try to take it out. Yes, this loop around. So with high energy, maybe we could take it out. If being able to do it, it would be this baryon decay that we destroy baryons. What would be a perfect energy source? That from any matter, like in this, in theory, we could squeeze a matter into black hole and wait until it evaporates and get empty square. So like 150 gram. A human we would need to just to destroy baryons from 0.02 grams to get energy a person is consuming over the whole lifetime. So in theory, the question is, can we do it? Can we destroy baryons? So is baryon number ultimately conserved, and it is varied in baryogenesis and Hawking radiation. So the question is, having this kind of structure, how to hit it somehow with lasers, with some particle physics, to get this loop around and take it out. Yeah? So maybe some shaking of this electric charge, or maybe some twisting to stimulate this proton decay. So if being able to do it, we would get something much better than fusion. But the question is it possible? But having a good model, we could simulate it at least. Yeah? So maybe try to design this kind of experiments.
Okay. Do you have some other questions? If not, let's thank our speaker again.
Thank you very much.
And we will see each other tomorrow for the first lectures by way. And Dima, unfortunately, his lectures will be in hybrid mode, but it will be transmitted here. We will be talking on Zoom. Thank you. Klikam to zatrzymywanie, nagrywanie i
Chyba coś zepsuli.